All right, today we're going to talk about probability of disjoint and overlapping events. So let's talk about specifically what we want to accomplish. We want to use the addition rule to determine how the union of two events affects probabilities of events occurring together. All right, so before we get into the addition rule, let's talk about unions and intersections. And so we all know the intersection of Homestead and Mary. It's right by where school is. So Homestead Road runs right through and is perpendicular to Mary. And so let's talk about the difference between a union of these two roads and the intersection of these two roads. So union is going to be everything on Homestead and everything on Mary. So I've highlighted all, and this of course goes further in this direction and in these directions. So it would be everything on Homestead and everything on Mary. And if we were to select something, we would use the word or. It would be one, it could be in one or the other, and it would still constitute as being part of a set of both Homestead or Mary, or the union of Homestead or Mary. Intersection is that part that's common to both. So, and then we designate intersection with and. So it's where Homestead and Mary both occur. So that portion of the intersection is probably pretty dangerous at 7:50 in the morning when everybody's trying to get to work and parents are trying to get their kids to school. So it's that intersection, that place that's common to both events. And so we're going to identify union and intersection with two different symbols. And the union is going to be this large U, as you can see here. And then the intersection is going to be that upside down U. So Homestead intersection of Mary is going to be this space here, and then the union of Homestead and Mary is going to be everything on Homestead and everything on Mary. For union we use or, and for intersection we're going to use and. All right, so now let's talk about the addition rule with respect to a Venn diagram. So let me walk you through this. So the rule says that the probability of A or B is going to be equal to the probability of A plus the probability of B minus the probability of A and B. And so we're going to take a look at this graphically so that you can understand what's going on. I have the probability of A as this circle, and the probability of B is this circle of events. And then the probability of A and B is this shaded region, let's call it 2 here. And it's shaded with kind of a yellow-red tone to it. So if we consider adding 1 and 3 together, then we've added this 2 part when we add the A, and then we add the 2 part again when we add the B, because this 2 area is in both A and B. So if we add A and B together, then we're adding the area for 2 twice. I have the area for A, which includes 2, and the area for B, which includes 2. But the reality is that 2 only needs to be counted once. So we're going to include everything for A and then everything for B except for 2. And the way that we can write that is to remove, since we're really double counting the area of 2, remove that area A and B once. So I have the probability of A, with that area of A, plus the area of B, this circle. And since I've already counted this area 2 in A, and then I counted it again when I considered the area for B, then now I'm going to remove one area for 2, and we're going to call that A and B. So the probability of A or B is equal to the probability of A plus the probability of B, minus 1 of the probability of A and B. All right, so union includes outcomes from both events even if they're different. And so if I wanted to consider the union of these two events, I have to add A and B and then subtract 2. All right. So another way to write A or B is A union B. So these are two equivalent statements. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Probability of A union with B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. All right, so we have to be able to, here's the or part, using or and and then here's union or intersection. And so we need to be able to say that these are equivalent equations. And you need to be able to go back and forth between these two as they're represented as you're being asked for information. All right, so let's talk about mutually exclusive events. Mutually exclusive events have no events in common. And so let's say it either is going to rain or it's going to be sunny. And so when it's sunny, it's not raining. And when it's raining, it's not sunny. So if one is happening, then the other cannot happen. And we call these events mutually exclusive or disjoint. So if A happens, then B definitely cannot happen. And if B happens, then A definitely cannot happen. And we can use this rule still to evaluate the probability of A or B. But we need to realize that because there is no intersection here, this probability of A and B is going to be equal to 0. So that leaves us with the probability of A or B is equal to the probability of A plus the probability of B. So for mutually exclusive, or another word for this disjoint events, then the probability of A plus the probability of B end up equaling 1 if we just have two possible outcomes. All right. So if two events are mutually exclusive, then the probability of A and B is equal to 0, because the probability of A or B is equal to the probability of A plus the probability of B. And there is no intersection. So going back to the prior Venn diagram, right here is where we have that A and B value. But when we don't have anything in common, there is no value for the intersection, then we call these mutually exclusive or disjoint events. And then the probability of A and B is equal to 0. So one way algebraically for us to tell, I mean, we can tell graphically here that there's no overlap, but algebraically or mathematically, for us to tell whether or not two events are mutually exclusive or disjoint, is to find out what the value of the probability of A and B is. If it is 0, then they're mutually exclusive or disjoint. If it is some number, then they are not mutually exclusive. That means it is possible for one to occur and also the other to occur. All right, so now we're going to move forward with this rule and the analogy and the Venn diagrams, and we're going to evaluate a situation where we have 30 people attending a beach party. 17 people, 17 of the 30, got sunburned, and 25 people were bitten by mosquitoes. The question is, if everybody either got sunburned and or was bitten by a mosquito, how many people got both sunburned and were bitten? All right, so here's the step we're going to go through. Steps. We're going to draw the Venn diagram. We're going to identify the values that correspond to each portion of the equation, and then we're going to determine the answer. All right, so we have our equation. Let's draw the Venn diagram. I have 17 sunburned and 25 mosquitoes. So I have here everybody who went to the party. I have 17 people getting sunburned and 25 people getting bitten by mosquitoes. But recall there are only 30 people who went to the party. So there has to be some overlap here, and that's what we're going to determine. All right, so I have 30 people going to the party, 17 sunburned, 25 people were bitten by mosquitoes. Now I can figure out what the value is for that content in A and B. We're no longer necessarily talking about probability yet. And we can figure out what that count is by doing a little algebra. 30 is equal to 17 plus 25. And so we end up seeing that this value for A and B ends up being equal to 12. So then 12 people were both bitten by mosquitoes and got sunburned. All right, so this brings us to our classwork for the first classwork problem for today. I'll give you a similar problem, and I'm going to pause here while you figure this out. So you're going to draw that Venn diagram. You're going to identify the values that correspond to each portion of the equation as written in the Venn diagram, and then write it out for the equation, and then you're going to determine the answer. So how many people got both sunburn and were bitten by mosquitoes? All right, so let's move on. All right, so now we're going to determine whether or not events overlap or whether or not they're mutually exclusive. So overlap is another term to say that they are not mutually exclusive. And so remember we said that if the probability of A plus the probability of B is equal to the probability of A or B, then the equations do not overlap. So let's go ahead and take a look at this. So I have the probability of A being 0.6 plus the probability of B is 0.2, and then the probability of A or B is 0.8. So since these two equal probability of A plus the probability of B equal probability of A or B, then that means the probability of A and B is equal to 0, which means that they do not overlap, or they are mutually exclusive. Or disjoint. So again, let's go back, or maybe we can write probability of A or B is equal to the probability of A, so our addition rule, plus the probability of B as it relates to probability, minus the probability of A and B, right? And if A or B is equal to A plus B, then this value is equal to 0, and they are mutually exclusive or disjoint. So what we're looking for is to see if A plus B is equal to A or B. And it does in this case, so we know that they're mutually exclusive. They do not overlap. Next one, probability of A is 0.3. So let's just write this here. 0.3 plus 0.2 is not equal to 0.44. So therefore, there is some overlap between A and B. All right? They are not mutually exclusive. They are not disjoint. All right? Probability of A, 0.5 plus probability of B, 0.1 equal to 0.6. All right, so these do not overlap. These are, say, mutually exclusive or disjoint. All right, and the last one, probability of A, 0.6 plus 0.4 does not equal 0.7. So then we know that these are probabilities or values which overlap. Okay, so we have mutually exclusive, disjoint, overlapping, disjoint, and then overlapping. Okay, this brings us to classwork 10.4.2. Okay, so let's talk about complements of events. And we've talked about this before. Complement of an event includes all the outcomes that are not in that event. So if A is an event, then the complement of that event is not A. And so if we talk about probabilities, the probability of not A is 1 minus the probability of A. And sometimes some books use this kind of nomenclature, probability of A with the C for a complement, so the complement of C. And these are equivalent expressions, probability of A with uppercase C, and then the probability of A with this bar here. Right? So the probability of not A is equal to 1 minus the probability of A. So as an example, if there's a 70% chance that it will rain today, the complement of that event is that it will not rain, and that value is 30%. Right? So 1 minus 70%, or 100 minus 70% is 30%. All right, so now we're going to expand our discussion about that Venn diagram, and we're going to include the total population now, because there are people who didn't go to the party, who didn't go to the beach, and we need to consider all those people sometimes. And so let's bring the scenario into play. In the previous example with the beachgoers, there could be a group of people who neither got sunburned or were bitten by mosquitoes, or who were not part of the party. So how do we represent this population? And so we're going to represent this as A or B, and then not A or B, and that's going to be equal to the total population. So I have A or B, and then the complement of A or B, and that equals the total population. So let's see how this plays out. So we're going to assign this to all the friends going to the party, and we're going to identify this visually with a box. And all the people inside the box represent some area or content. And some of those people didn't get sunburned and didn't get a mosquito bite even though they went to the party. All right, so sometimes with overlapping events, there's a superset of population that needs to be considered. In order to determine this, ask yourself if the population in question is entirely within the given set. So if we have some people who didn't get sunburn or a mosquito bite, then we need to consider this other population. All right, we're going to stop here and we'll come back.